Okay, in this video I'm going to be demonstrating the use of the ProEngineer ProMechanica finite element package to solve for stress concentrations for a flat plate with a hole drilled through the flat plate with bending moments applied to that flat plate as shown in this picture. And so I have created geometry that will let us then come back to this figure and compare our stress concentration computed from ProEngineer to stress concentrations computed from this chart. So let's move the chart out of the way. And just as in class, I've already created the ProEngineer geometry model. I did change it up a little bit to fit the axes of the stress concentration chart a little bit better. This is a 1/2 inch radius hole or a 1 inch diameter hole. This is a 1/2 inch edge in this direction, and this is a 1/2 inch thickness through the thickness, again, to make it fit the chart just a little bit better. So here's the part. I'm not going to go into anything related to creating the part. But now to go into Mechanica, I will go Applications, Mechanica. Okay, and because I've already taken this model into Applications Mechanica before, it did not show me my unit systems. You need to be very careful to make sure you're working with appropriate unit systems. Just to check, let's take a look at the model setup. Right now it is a 3D model, and that's what I'm going to want to be working with, so I'm going to go ahead and cancel and keep that as a 3D model. Now, as compared to the picture from the stress concentration chart A15-2, I've created a quarter model, and I think that is going to be sufficient. What I need to do is constrain the model, load the model, assign material properties, all of those kinds of things. So first thing I'm going to do is constrain this surface, and I can actually pre-select the surface. I'm going to constrain that surface using this constraint or displacement constraint. And looking at my coordinate system, I see that the x direction is along this line. And so I'm going to say that this thing cannot move in the x, but it can move in the y and the z on that surface. I'm going to do the same kind of thing on this surface down here, pre-selecting it, displacement constraint. And I don't want that surface to move in the y direction. Both of those will then, but I will allow them to move in the x and z direction. Both of those are maintaining the axes of symmetry that were required for me to be able to use a quarter model instead of an entire model. Okay, so with these two constraints in place, the model cannot move left-right because of this surface. This model cannot move fore-aft because of this constraint, but the model can still move along the axis of the hole. It can move parallel to this edge right here. And so I also need to constrain it from moving in that direction. And what I've decided to do is simply take an edge, that edge, and say that that edge can't move in the z direction. And so I'll go to the constraints. It already sees that I have the edge, and I will constrain that so that that edge cannot move in the z direction, but that edge is free to move in the x and y directions. Those are my constraints. Now I need to put some kind of a loading on this thing to produce a bending moment. If I were to attempt to put some kind of a shear loading on this thing, this no vertical motion constraint would actually keep me from moving at all due to the load. Wouldn't help at all. What I really want to do is place a bending moment on this surface about the y-axis. Let's turn off some of these other things so we can see our coordinate system a little better. So I want a bending moment on this surface about the y-axis. So let's go take a look at that. I'll go ahead and select the surface, and I'm going to go to Loads. Okay, so it's already got the surface selected. And if I attempt to put a moment in the y direction, and I'm just going to arbitrarily pick 100 inch-pounds. If I attempt to place a moment on there, and I preview it, you see these moment vectors. Those moment vectors are pointed in the right direction. Let's go run this model. So I'm going to say OK. And I will then go to my analysis tool, File, New Static Analysis. let's go with multipass adaptive. Let's bump the convergence down for now to 5%. And let's go ahead and move this up to 9, because this doesn't take very long to run at first. And I will say OK. We will do a run, yes, no, and view the results window. And this one has already completed. Let's see. No, it says it ran with a fatal error. One or more surfaces have a load but are not part of any element. This thing is very much unhappy. Let's go try this a little bit differently. I'm going to get rid of this displacement constraint. No, I've got to have that displacement constraint. Okay, well, I was trying to show something that I already knew was a problem, because I know, and in fact, if you read the help system, that you can't place moment loads simply on the surface of a solid. It's simply against the rules. It's not that it doesn't make sense mathematically, because I think it makes perfect sense. I don't know why ProEngineer won't let you place a moment load on a surface like this. It makes total mathematical sense to me. I was hoping to show you that nothing would happen, but it appears that this thing is totally unhappy. So let's proceed ahead. Let me fix this load, and then we'll see if things are happy. So what I'm going to do is delete the loading and show you how to do it right. And what I'm going to do is select this surface again, and I'm going to go into the loading, and I'm going to go to advanced. This is absolutely required. If I want to put a moment load on this surface, I can't do it the naive way. I must go to advanced. I must go to total load at point. Okay, so on this surface, I'm going to place a moment that causes a total moment load at some point to be whatever number I specify. It'll then figure out how to distribute loads to make that happen. So I need to select the point, and because I'm placing moments on this surface, and it is moments, I can actually pick any point I want, so I'm just going to pick that point. It was really arbitrary. And now I want a net moment about the y-axis of 100 inch-pounds. Now, if I preview this, it's going to look a lot different. Okay, look at my preview loading. Now, that's actually what I prefer to see. And what it's going to do is create a series of loads on the surface that are axial loads, but those axial loads in the end will, if I were to sum moments about that point, the sum of all of these loads will produce a moment about that point of 100 that I specified, and is a moment of 100 about the y-axis and no other direction. So I'm going to create those loads. Okay. Actually, another reason I probably didn't run earlier, I wasn't paying enough attention, was I didn't have any materials. So I need to bring materials into this thing. I already have steel there. No, that's fine. I didn't mean to do that. Cancel, yes. Steel, okay. And now I do have materials in this part. And I think I'm ready to run, and I think this thing will run. Let's look at, though, very quickly at the notation of this load. It shows a double, it's hard to see, but this is a double-headed arrow showing a moment of 100 in the y direction, total at that point caused by loads on this surface is what that thing means. Now let's go to analysis, run, yes, no, and let's see what happens. Pass 3, 6, 9, or whatever, lots of passes, and analysis converged to within 5%. Okay, go look at the results. I want to see the deformed shape to help me understand it. Okay, and show. And what's happened is, by creating this bending moment on this surface, because of the loading, it's caused this surface to tilt, as it should. This surface may no longer be planar. I don't know. But it caused this surface to move upward, but this surface remained both planar and did not travel in this x direction. Okay? And this surface should have remained perfectly straight and perfectly flat on this surface right here, and it did. Now let's see what kind of stress numbers I'm getting. If I go to Info, Model Maximum, it is showing me a maximum stress occurring at this corner of 6,390 psi. Now, to make this thing work out, we've got to calculate what we think what the nominal stress should be in bending along that line. And the nominal geometry is 0.5 inches this way, 0.5 inches that way. So let's just bring in a calculator and say that BH cubed over 12 is moment of inertia. Both B and H are 0.5. So 0.5 y to the x 4 equals divided by 12 equals. That should be my moment of inertia. So now I want to do MC over I. My moment was 100. And instead of dividing by I, I'm going to multiply by the reciprocal of I. So where is that 1 over x key? This is 1 over I times the moment, 100. And then c would be the distance from the neutral axis to the point that I care about. This total distance is 0.5, so c is going to be 0.25, so times 0.25. So my nominal stress of 4,800 psi existing along this line as compared to 6,390. So I'm going to take that, divide by 6,390 is equal to that, and I'll take the reciprocal of that, and that should be my stress concentration. A stress concentration of approximately 1.33. Going back to the diagram, I have a D of 1 inch, and I have a W of 2 inches, so that D over W is 0.5. I'm on this vertical line. Then this says D over H. H is shown right here, which is a value of 0.5, and D is 1 inch. So D over H is 2. So my curve would be on this vertical line and extending that 2 line on down. And so I would estimate that that 2 line would be somewhere below this line, right in the neighborhood of there. Now, attempting to read that would give me, and let's go ahead and zoom in on this a little bit. Let's go to 150% and then scroll. Look at this a little more carefully. Okay, so I think that I am, let's see, 0.5, and I'm up in this region, I suppose. Let's see. Yeah, this is the right one. I'm up somewhere right around the 1.4. I got a 1.33 on that 2 line, so I'm in the ballpark. It's not superb. What we'll do in the next video is play with this a little bit more and just see how the answer changes, the 1.33 changes, or more specifically, how does the 6390 change as I play with elements. So I'm going to end this one here, and then we'll come back to the next video and start playing a bit more.